So in this second lecture, I will discuss independence. So here is the where probability becomes different from measure theory. We will introduce this new concept of independence. So remember that we are working with a measure space. So we have an abstract space, omega. We have a sigma algebra of subsets of omega and a probability measure defined on this space. Now, if a subset A of omega belongs to the sigma algebra F, we will call A an event. And here is the definition. If we have a family A1 up to AN of events, they are said to be independent if the following holds. If for all subsets of 1n, so for all n1 up to np, subset of 1n, and here I'm assuming that nj is different from nk if k is different from j. The following hold: the probability of the intersection from k running from 1 up to p of a n k, that this is equal to the product. So k from 1 up to p of the probability that a n k. So if you take any subset, if the probability of the intersection is equal to the product of probabilities, you say that these events are independent. Now I will extend this definition of independence to random variables. So if I have a family x1, xn of random variables, I would say that these random variables are independent if for all b1, bn elements of the Borel sigma field B, we have that the probability that the intersection from 1 up to n, that xj belongs to bj, well, that this probability is equal to the product of probabilities. So if this holds for all b1, bn in the Borel sigma field, then we say that the random variables x1, xn are independent. And we can extend this definition to any family x alpha of random variables. So now suppose that we have x alpha for alpha in I can be any set, a family of random variables. We will say that this family is independent if, well, for any finite subset, so for any n and for any alpha 1 alpha n subset in I, alpha j different from alpha k if k is different from j. So if you take any finite subset of indices in I, the family x alpha 1 up to x alpha n are independent. So with the first definition, we can extend it to an arbitrary family of random variables. So we'll say that they are independent if any finite family is independent. A remark before we proceed is that, well, assume that the random variables x1, xn are independent. Then what I claim is that if you take any subfamily, you get independent family. So take any p less than n and consider the family x n1 up to x np. Here again I'm assuming that n1 nj is different from nk if j is different from k. And what I claim is that xn1, xnp are independent. And why is that so? Well, we have to prove that this family is independent, so you choose sets B1, BP in the Borel sigma field, and you have to consider the probability of the intersection from j equal to 1 of p of x and j in Bj. But you can write this probability now as the probability of the intersection of I equal from 1 to n of xi belonging to ai. And here ai, well, you choose ai will be either bj if I it's equal to nj for some j. So among the i's, well, there are a few ones which belong to the set n1, np. So if I it's equal to nj for some j between 1 and p, you define ai as the set bj, which is the one which appears here. And if I does not belong to the set n1 np, you define I to be R, which is a Borel subset. And with this definition, you see that, well, this intersection, it's exactly equal to this intersection. Now you use the fact that the random variables x1, xn are independent to write this probability as the product of I equal to 1 up to n of the probability that xi belongs to ai. But now if I does not belong to n1, np, since ai is equal to r, this probability is equal to 1. So that becomes the probability of j from 1 up to p of the probability that x and j belongs to bj. And therefore, from this identity, you conclude that the family xn1, xnp is a family of independent random variables. So in the first lecture, we introduced the concept of random variable. Now, we will introduce the concept of a random vector. Well, if instead of taking r, we take r to the power n, let me denote by Bn the family of subsets of Rn, which is the smallest sigma algebra which contains all the open sets of Rn. So this is the sigma algebra called the Borel subsets of Rn, and it will be denoted by Bn. So Bn is the Borel sigma algebra of Rn, which I repeat, is the smallest sigma algebra which contains the open sets of Rn. And we have, therefore, a measure space, omega f and p. Well, I'll say that a function x from omega to Rn is a random vector if, well, it's a measurable function if we take in Rn the Borel sigma field and in omega the Borel, the sigma algebra f. So this means that this is a random vector if for all sets A in Bn, the inverse image by x of A belongs to f. So this is the definition of a random vector. And now, as before, so remember when we introduced random variables, we introduce the distribution function and the distribution measure. Here again, I can define the distribution function. So the distribution function will be now a function f. Let me represent by fx to say that it's the distribution function of the random vector x, which is a function from Rn to the interval 0, 1, which is defined as follows. Well, fx of x, so now x it's a vector in Rn, so this is equal to the probability that x, so let me write x, which is a random vector, as the vector x1, xn. So these are the coordinates of the vector x. So this is the probability that x1 it's less or equal than x1, xn less or equal than xn. And where also the point x is simply the vector x1, xn. So this is the distribution of, this is the definition of the distribution function associated to a random variable x, a random vector x. And now we have the concept of distribution measure, or probability distribution measure, if you wish. And this is a measure which will be represented by mu x. So this is a probability measure on the set Rn, on the measure space Rn Bn. And how is it defined? If you take an element A in Bn, you define mu x of A as the measure with respect to P of the inverse image of A by x. So this is x minus 1 of A. And remember that we are representing this probability by the probability that x belongs to A. So we defined the random vector. We introduced the distribution function of a vector and the probability distribution measure of a random vector. So now suppose that we have x, a random vector, of course x, so it's a vector, it's x1, xn. Each of the coordinate, it's a random variable. So associated to this random variable, we have the distribution functions fxj and the measures mu xj. So these are the distribution function of the random variable xj, and this is the probability distribution measure of the random variable xj, where xj is a coordinate of the vector x. And I have a lemma. I'm claiming that the random variables x1, xn, so assume that you have a random vector x whose coordinates are x1, xn, and what I claim is that x1, xn are independent if and only if the distribution function of the random vector x at x1, xn, it's equal to the product of the, from j from 1 to n, of the distribution functions of the random variable xj at xj. So I will leave the proof of this lemma as an exercise. There is a direction which is obvious. So if x1, xn are independent, well, this probability, by definition, is the probability that the intersection from 1 up to n of that xj, it's less or equal than xj. So this is the definition of the distribution function of a vector. Now, we have seen that since the random variables xj are independent, the probability of the intersection is equal to the product of the probabilities. And now, by definition of the distribution function of the random variable xj, this is equal to the product of the distribution function fxj at xj. So we have here the identity which was claimed here. Now, so in this direction, the proof it's quite obvious. So what needs an argument? It's the converse. And the converse, well, what this identity is saying, the identity is saying that, well, that this is equal. So what we know from this identity, it follows from this identity that just rewriting the definition of the distribution function on both sides is that this identity holds. Well, but to prove that x1, xn are independent, what we need to prove is something stronger. What we need to prove is that if you take the intersection from 1 to n of xj belonging to a Borel set bj, that this is equal to the product from 1 to n, that the probability of xj belongs to bj. So what we know is that this identity holds for sets, for very special sets bj, for sets bj which are semi-infinite interval xj. So you know that this identity holds for a special class of sets, and what you want to prove is that it actually holds for all Borel sets bj. And this is, well, there is a classical way in proving such statements. So there is a classical way in which you can extend an identity which holds for special sets to all sets which belong to a sigma algebra. And so this is a classical method in measure theory, and therefore I leave it to you to prove that indeed, if the distribution function of the vector is given by the product of the distribution functions of the coordinates, then the random variables are independent. We can rephrase the previous lemma in terms of probability distribution measures and say that x1, xn, the random variables x1, xn are independent if and only if the probability distribution measure of the vector x of a set b1 times bn, that this is equal to the product from 1 to n of the probability distribution measures of xj of the set bj. So this is almost a tautology. I leave it to you to check. So we have also a way to identify independent random variables from the probability distribution measures. So I leave it to you as an exercise again, just to check that this lemma holds. We have now two important theorems which are both very easy to prove. So the first theorem reads as follows. Suppose that you have x1, xn independent random variables, and that you have measurable functions f1, fn. So these functions fj are functions from R to R, and I'm assuming that they are measurable. And always I'll be taking, as I said before, the Borel sigma algebra associated to R. Then what I claim is that the random variables f1, x1, fn, xn are independent. So proof, it's almost a one-line proof. To prove that these random variables are independent, what we need to check is that the probability of the intersection from 1 to n, that fxj, fj, xj belongs to bj, that this is equal to the product. And here you take b1, bn sets in the Borel sigma algebra. So these are Borel sets. So now, what is that fj, xj belongs to bj? This is the same thing as saying that xj belongs to the image inverse of bj. Right, saying that fj, xj belongs to bj, it's the same thing as saying that xj belongs to the inverse image by fj of bj. Now, since fj are measurable functions and bj are Borel sets, these sets are Borel sets. And since these sets are Borel sets and the variables x1, xn are independent, the product, the probability of the intersection, it's equal to the product of the probabilities. So this is equal to the product from 1 to n of the probability that xj belongs to the inverse image of bj. And saying that xj belongs to the inverse image by fj of bj is the same thing as saying that fj xj belongs to bj. And therefore, we have, by looking at the first term and the last term, proved that the probability of this intersection is equal to the product of the probability. And since this holds for all Borel sets b1, bn, we have that indeed the random variables f1, x1, fn, xn are independent. Now we have a second theorem with the same assumption that x1, xn are independent random variables. But now I will consider a different context. I have x1, xn1, so let me take n1 less than n2. So this is larger than 1, less than np, and np is equal to large N. So we have xn up to xn1, then xn1 plus 1 up to xn2, and so on. So here we have n1 random variables. Here we have n2 minus n1 random variables until the end, in which we have x np minus 1 plus 1 up to x np, and this is, remember, xn, because np is equal to n. And here we have np minus 1 random variables. And now we have a function f1. So n1, n2, np are fixed. They satisfy this condition. And we have Borel functions, but now f1, it's a function from R n1 to R. And generally, fj will be a function from R nj minus nj minus 1 up to R. And this for j between 2 and p. So we have p different functions, f1 up to fp. I will assume that they are all measurable. So in R, again, I'm taking the Borel sigma algebra, and in Rj or Rk, I'm taking the Borel sigma algebra bk. and I'm assuming that these functions are measurable with respect to these sigma fields. And now what I claim is that f1 of x1 up to xn1, f2 xn1 plus 1 up to xn2, and so on up to the last one, which is fp n x n p minus 1 plus 1 up to x and p, that these p random variables are independent. And I leave it to you as an exercise. So the proof, it's almost identical from the last proof, and so I can leave it as an exercise. I hope you're not too bored by this lecture, but you'll see in the next lecture many applications of this concept of independence. So you'll see it's very rich, and the applications are quite nice. So here is a first important theorem. Well, the other ones were important, but the proof were trivial. This one is less. So we have a measure space, omega f, and a probability. And in that space, you have two independent random variables, x and y. And I'm assuming that either x and y are positive, or I will assume that they are integrable. So which means that the expectation of the absolute value of x is finite, and that the expectation of the absolute value of y is finite. Now, what I claim is that in this case, x times y it's integrable, and the expectation of x times y it's equal to the expectation of x times the expectation of y. So again, x and y are independent, they are integrable, then what I claim is that the expectation of the product is equal to the product of the expectations. Proof. Now the proof relies on the way in which you construct the integral. So this is the integral of x times y, and remember that how you define the integral of a random variable, of measurable function, well, you first assume that this measurable function is a simple function. Then, well, you have an equation for the integral. You show that it doesn't depend on the way you choose your simple function. Then you take a positive function and you show that it can be approximated by a sequence of increasing simple functions, and you define the integral as the limit. You show that this definition is well defined. And finally, when you take a random variable which has positive and negative values, you define the expectation as the expectation of the positive part minus the expectation of the negative part. So here we are going to prove this identity step by step by following the definition. So first I will assume that x and y are simple functions or simple random variables. This means that x and y take only a finite number of non-negative values, so simple random variables which are non-negative. So here I'm assuming that x and y take only non-negative values, so that x it's actually equal to the sum from 1 up to n of xj, and it takes the value xj on some set, on some event ej. So ej it's an element of the sigma algebra F, and I'm assuming that x can be written this way, where the xj, the real number xj, are non-negative, and that y it's also equal to the sum from 1 up to m of yk chi fk. And here also the fk's are elements of the sigma algebra, and yk are non-negative. And under the conditions that x and y are independent, I'll prove that this identity holds. So you write x and y, the expectation of x and y. Well, x is given by that, y you take the product, you have a sum, so you use the linearity. The linearity tells you that this is equal to a sum of j from 1 up to m, a sum from k from 1 up to m, xj, yk, and then you have the expectation of chi ej, chi fk. Of course, I can assume that all the values xi are different from xj. The same thing for the y's. Otherwise, I could have glued together some of the sets ej's, so I can assume that. So this is the probability that, so x it's equal to the set, so this is the probability, ej corresponds to the set at which x takes the value xj. So first, let me write this probability as the probability of ej intersection fk, right? Because the indicator function of the set ej times the indicator function of the set fk, it's equal to the indicator function of the set ej intersection fk. The expectation of the indicator function of a set A, it's equal to the probability of this set. So this shows that this probability, this expectation, it's equal to this probability. But now the set Ej, it's equal to, correspond to the set of omegas at which x, it's equal to xj. So this probability, it's equal to the probability that x, it's equal to xj, y equal to yk. Now let's use the fact that x and y are independent to write this probability as the probability that x is equal to xk times the probability that y is equal to yk. So this is just by independence. And now, well, x equal to xj, it's the probability ej. Y equal to yk corresponds to the set fk. So we proved that this probability is actually equal to the probability of ej intersection times the probability of the set fk. So let's continue here. Up to the moment we proved that the expectation of xy it's equal to the sum in j, sum in k, xj, yk of these two probabilities. So I can rewrite this as the sum j from 1 up to n of xj, the probability of ej, times the sum from k from 1 up to m of yk, the probability of fk. And now I can replace ej by the indicator of ej, then use linearity again to get that this sum is equal to the expectation of x, and that the second sum is equal to the expectation of y, from which we see that we proved that the expectation of xy it's equal to the expectation of x times the expectation of y. So we proved the theorem in the case in which x and y are simple random variables which are non-negative. Now I want to extend this identity to non-negative random variables. So let me take two random variables x and y which are non-negative, and I want to prove this identity for these two random variables. So we know from measure theory that we can find a sequence xm which are simple non-negative simple random variables which are increasing to x. And the same thing for a family yn of non-negative simple random variables which are increasing to y. So it follows from these two observations that if I take xn times yn, the product of two non-negative simple random variable is a new simple non-negative random variable, and this sequence of simple random variables, it's converging to xy. It's increasing and converging to xy. So by the monotone convergence theorem, we have that the expectation of xy, it's equal to the limit in n of the expectation of xn yn. Right, seems this is just from the fact that xn yn are increasing to xn y and that xn and yn are non-negative. So this is the monotone convergence theorem. Now, as I said, xn and yn are simple random variables, non-negative, and we proved already the theorem for these variables. So this is actually equal to the limit of the expectation of xn times the expectation of yn. And now, again, by the monotone convergence theorem, since xn is converging, increasing to x, and yn is increasing to y, the expectation of xn by the monotone convergence theorem converges to the expectation of x, and the expectation of yn converges to the expectation of y. So this is equal to the expectation of x times the expectation of y. And so this proves the theorem in the case in which x and y are non-negative random variables, which is the first case which I stated. So now this one is proved. It remains to prove the case in which both x and y are integrable. Now let's consider the general case. So we are assuming that the expectation of the modulus of x and the modulus of y are finite, and let's prove this identity. So xy, I can rewrite x and y as the positive part of x minus the negative part of x times y plus minus y minus. So now you distribute this product and then you use the linearity of the expectation. You see that all this is well defined because since the absolute value of x and the absolute value of y are finite, we know already that the expectation of x plus, say, y minus are finite, because x plus is the function fx maximum 0, and this is a function. So what I'm saying is that if you take the function f from R to R, which to a point x takes its positive value, which is the maximum between x and 0, x plus is fx. And you can also represent y minus as g of y, where g now takes the negative value of a number y. So now, since x and y are independent, by a previous theorem, you know that fx and gy are independent, And since x plus and y minus are both non-negative, since they are independent, you know that this expectation is equal to the expectation of x plus times the expectation of y minus. This is the second part of the proof of this theorem. And since x and y are integrable, these two expectations are finite, which proves that this random variable, which is non-negative, has finite expectation. So you know that each of these products, it's a product so that when you distribute these products, you get random variables which are all integrable. So you can use linearity to say that this expectation is actually equal to the expectation of x plus y plus minus the expectation of x plus y minus and let me continue here, minus the expectation of x minus y plus plus the expectation of x minus y minus. Now you can repeat the argument I just gave to say that these random variables are all independent and use the second part of this theorem, which tells you that in this case the expectation is equal to the product. So you'll get here the expectation of x plus times the expectation of y plus. I won't write the other three terms. And once you wrote it in this way, you can reconstruct the expectation. So that will become the expectation of x plus minus the expectation of x minus times the expectation of y plus minus the expectation of y minus. And now, since the random variables xy are integrable, this is exactly equal to the expectation of x times the expectation of y. And from that you conclude that indeed you have this identity, and again this is a very used method in measure theory to prove identities of expectations or of integrals. You started from a very simple one and then you extend it to more complicated ones. So this is a standard method to prove identities which we learned in measure theory, and here it allows us to prove this theorem, which I recall states that if x and y are independent random variables which are integrable, then the expectation, then xy it's integrable, and the expectation of xy it's equal to the product of the expectations. Let me give you a second proof of this theorem, and which is based on the following observation, which I leave it to you to prove. So assume that you have a random vector x from omega to Rn, and we have defined with the probability distribution measure mu x, which is a measure on the set Rn Bn. Now, what I claim is that if you have a function f from Rn to R, such that the expectation of f of the absolute value of f of x is finite, so this means that the integral of fx dp in omega is finite, then the following identity holds: the integral over omega of fx dp, that this is equal to the integral over Rn of fx mu x dx. So this is a measure in Rn. This is a function which is defined in Rn. So what I claim is that under this assumption that this function now it's integrable with respect to mu x, and that this identity holds. So again, you know that this identity holds by definition of the measure mu if I take f to be the indicator function of a Borel set. But what we are claiming here is that you can extend this identity from indicator functions to general measurable functions under this assumption. So I leave it to you to check this identity and as an exercise, and I will prove the previous theorem under assuming that you already proved, assuming that we know this identity. So again, we want to prove the theorem that if x and y are random variables which are independent, and if they are integrable, we want to prove that the expectation of xy is equal to the product of the expectations. So let's prove that using the previous identity. Here we have a random vector, which is xy. So I will represent by mu xy the probability distribution measure of the vector x and y. And we have seen that since x and y are independent random variable, actually this measure, it's equal to the product of the measures. So it's equal to mu x dx, mu y dy. And now we have a function from R2 to R, which associated to the pair xy, the value x times y. And by, these assumptions, we know that f is actually integrable. So we can apply the previous theorem and say that the expectation of xy, which is the expectation of fxy, so by definition, so f is this function, so this is f xy mu xy dx dy. So this is the identity between that we mentioned in the previous take. Now I can replace fxy by xy, and I can use the fact that they are independent, which tells me that this measure is actually the product measures. So this is so that's an integral in R2 of xy, mu x dx, mu y dy. And now, by Fubini, we have that this integral is actually x mu x dx times the integral in R of y mu y dy. And now, we can go back and say that x mu x dx by the previous take, it's equal to the expectation of x, and y mu y dy, it's the expectation of y. Maybe I haven't been so precise about why we are allowed to use Fubini's theorem. Well, we can go step by step. First, assume that x and y are non-negative. If x and y are non-negative, this means that this measure is concentrated on R plus and this one on R plus. Now, these two x and y are non-negative, and therefore we can use Tonelli's theorem, which tells us that this product is equal to this integral, it's equal to this product. So this is in Fubini's case when the variables or the functions are non-negative. So we know that this identity holds for non-negative random variables. Now we can prove that if you take x and y satisfying these two inequalities, then the product x and y, it's integrable. And for that, we just repeat. So for that, what I'm saying is that x and y is integrable, so that this expectation is finite, because this is equal to the expectation of x times the expectation of y. Now x and y are independent. This shows that the modulo of x is independent from the modulus of y. Now this is a non-negative random variable, this is a non-negative random variable. They are both non-negative, so we already proved this identity in this case. So this is equal to the expectation of x times the expectation of y. And this is indeed finite by assumption. So this shows that x and y, the product of x and y, it's indeed integrable under our assumptions, and therefore we are allowed to use Fubini's theorem. So that provides a second proof of the theorem, a more direct proof by using a previous result, which tells us that if x and y are independent, then the probability distribution measure, it's actually a product of probability distribution measures. I want to complete this lecture by giving you an example of an infinite family of independent random variables. So for that, I will start from a family, a countable family of measure space. So let's assume that for j larger than 1, we have abstract spaces omega j. They might be all equal, sigma algebras fj, and probability measures pj. Now I want to consider the space omega, which is the product of the omega j's. So the elements of omega are sequences in which the first coordinate belongs to omega 1, the second to omega 2, and so on. So this is my space omega, and I want to define a sigma algebra in this set omega and a measure. And for that, I'm just recalling you Kolmogorov theorem, which allows you to extend or to construct a measure in an infinite product space. And how does it work? Well, we will consider what's called the cylinder functions, cylinder sets in this space. The cylinder sets will be sets of the following form. It's A1 times AN times omega n plus 1, omega n plus 2, and so on. So these sets will be called cylinder sets, in which, of course, A1 it's an element of F1, A2 an element of F2, and AN an element of Fn. So if a subset of omega can be written as a product of A1 times A2 times AN, and starting from some index n, then we take the whole spaces, omega n plus 1, omega n plus 2, we call that a cylinder set. And now I leave it to you to check. So let me call S the family of cylinder sets. My claim is that this family is a semi-algebra. So I leave it to you to check that it's a semi-algebra. Then I will define a probability in S. So I take an element of S. This element, it's by definition a product of A1 times AN times omega n plus 1 etc., well, I'll define, so this is a definition, as the product from 1 to n of pj aj. So this is my definition of the probability of a cylinder set. Now I claim that this probability is well defined, and moreover that it's sigma additive on the semi-algebra S. So this is the main step in this construction. So this is the main obstacle, and I leave it to you to check, or you can see at the notes, I'll give you a reference for this theorem. So I claim that it's sigma additive, and therefore we can use Kara-Theodori theorem to extend this probability to the sigma algebra generated by this semi-algebra. And this I will call that F infinity, or the product of the FJs. So I will represent the sigma algebra generated by the semi-algebra of cylinder sets by the symbol J1, product of 1 to infinity of the FJs. So in this way, I constructed a probability on this space omega endowed with this sigma algebra. Let me give it the name, a simple name, F infinity. So now we have a new space, which I call omega, a sigma algebra F infinity, and a probability P. And here I summarized in 5 minutes or in 2 minutes Kolmogorov theorem, extension theorem, which is based on Kara-Theodori extension theorem. So once we have that, and mind that it's very important that these are probability measures, because actually what's implicit here is that I'm taking Pn plus 1 omega n plus 1, Pn plus 2 omega n plus 2 in this product, but these are all equal to 1. Now, I will define on these space random variables xj. So xj, it's a function from omega to r, in which, say now that I'm taking a special case in which all these omegas, j's, are equal to r, and all these fj's are equal to the Borel set. So in this case, here my triple becomes the sequence, the infinite sequence of real numbers, R infinity. This is what's called the sigma algebra generated by the cylinder set. It's the Borel sets of R infinity, and P, well, P it's the measure which we just constructed. So in this case, let me define these random variables, xj, going from R infinity, say, to R. And you take a sequence omega, this is giving you the value of the jth coordinate of this sequence. And what I claim is that these random variables are independent. First, see that they are indeed random variables because, well, if you take a Borel set in R, you take its inverse image by xj, the inverse image of a Borel set by j, it's simply equal to, let me call that omega 1 up to omega j minus 1 times b times omega j plus 1, and so on. So this actually is a cylinder set. Right, in our example, omega 1 it's R, omega 2 it's R, omega j minus 1 it's R, but it's easier to understand if I use the previous notation. So you see that starting from j plus 1, I have all the sets omega n, and therefore that not only this is a measurable set, but it's actually a cylinder set. And this proves, therefore, that the inverse image of a Borel set indeed belongs to the sigma algebra F infinity, and therefore that xj is a random variable. So I further claim that these random variables are independent, and to prove that, well, we have to compute what is the probability that x1 belongs to b1, xn to bn, right? So let's fix n, and let's fix Borel sets b1 up to bn, and let's compute this probability. So by construction, this is the probability of the set b1 times b2 times bn times omega n plus 1, omega n plus 2, and so on. Now this is again, this is a cylinder set, and on the cylinder sets we have a formula. This is equal to the product g1 up to n of the probability j of bj. But the probability j of bj, this is equal to the product from 1 up to n of the probability that xj belongs to bj. Right? Because the probability that xj belongs to bj is the probability of the set omega 1, omega 2 up to omega j minus 1, bj, omega j plus 1, omega j plus 2, and so on. And this probability, by definition, it's pj beta j, because all the other ones will give you 1. And therefore, from this identity, you see that indeed the probability of the intersection, it's equal to the product of the probabilities, and therefore that these random variables x1, xn are independent, and therefore by definition, actually the family xk, for k larger than 1, it's a family of independent random variables. So this proves that, well, I restricted myself at some point to the sets R with the Borel sigma algebra, but it tells us that if we start with a countable family of probability measures defined on the Borel sigma algebra, you can define a new measure on R infinity, whose marginals are equal to mu j, and for which the coordinates are independent and distributed according to the mu j's from which you start. So you can in this way construct a countable sequence of independent random variables with assigned probability measures.